Hello everyone. Here I'm not going to read and explain the whole book. I'm going to share all the important concepts required for you all to know. So let us start with a new topic, operating systems. So before we enter into the depth, let us know what operating systems are. An operating system is a program that manages the computer hardware, or in other words, we can say that an operating system acts as an intermediate between the computer user and the computer hardware. Some OS, also known as operating systems, are designed to be convenient, others to be efficient, and others as combination of the two. Now let us know what an OS does. So here we come to know what operating systems actually do. So what do you think an operating system does? Firstly, let us know the operate components of a computer system. Firstly, a computer system can be divided into four components: the hardware, OS, the application, programs, and the user. An OS does not perform any useful function by itself. It simply provides an environment within which other programs can do useful work. So this is all about the basic. So let us know about the user view. The user's view of the computer varies according to the interface being used. For a personal computer or PC consisting of a monitor, keyboard, mouse, and system unit, the system is designed for one user to monopolize its resources so as to maximize the work that the user is performing. Here, OS is designed for ease of use. In other cases, a user sits at a terminal connected to a mainframe or mini computer. Other users are accessing the same computer through other terminals. These users share resources and may exchange information. The OS in such cases is designed to maximize resource utilization to assure that all available CPU time, memory, and I/O are used efficiently, and that no individual user takes more than her fair share. So this is all about user view. Here you can see the text of user view. If you want, you can go through it. I have just done the basic brush up of what is written over here. Next, let us come to system view. System view from is nothing but the computer's point of view. The OS is a program most intimately involved with the hardware. Here, OS can be considered as a resource allocator. A computer system has many resources that may be required to solve a problem, such as CPU time, memory space, file storage space, iOS, etc. The operating system can act as the manager of these resources. Now let us define OS. How can we define OS? The fact is that we actually can't define an OS as we have no adequate definition for an operating system. OS exists because they offer a reasonable way to solve the problem of creating a usable computing system. Here it's just given all the definition, and over here you can see 1 KB is how many bytes, 1 MB is how many KBs or how many bytes, or 1 GB, this, that, and all. So this is here with the completion of the first part of introduction. Thank you.
Computer system organization and computer system operation in an operating system (OS) are fundamental concepts that underpin the functionality and management of modern computers. Computer system organization refers to arrangement of hardware and software components that make up a computer system and how they interact with each other to perform tasks efficiently. The key hardware components include the central processing unit (CPU), memory, RAM, storage devices, example hard drives, solid state drives, input/output devices, example keyboard, mouse, monitor, and networking interfaces. The OS plays a crucial role in coordinating these components and managing their resources to ensure smooth and secure operation. It provides a layer of abstraction that shields application software from the complexities of hardware, allowing programmers to develop software without worrying about low level details. Computer system operation, on the other hand, deals with the execution of programs and the management of system resources by the OS. When a user runs an application, the OS is responsible for loading the programs into memory and allocating the necessary resources, such as CPU times, memory spaces, and I/O devices, to the application. The OS also enforces security and access controls to prevent unauthorized access to sensitive data and resources. It facilitates communication between different components and applications, allowing data to be transferred between programs and devices. In an OS, storage structures are essential components that manage the organization, allocation, and retrieval of data on storage devices, such as hard disk drives, solid state drives, and other secondary storage media. These structures play a crucial role in ensuring efficient data storage, retrieval, and overall system performance. Let's explore some common storage structures. File systems. The file system is the most familiar storage structure to users. It organizes data into fields and directories, providing a hierarchical structure for organizing and accessing data. The file system is responsible for managing file metadata such as permissions, timestamps, and file locations on the storage device. Blocks and clusters. Storage devices divide the data into fixed size blocks or variable size clusters. These blocks are the smallest addressable units on the storage medium, making data storage and retrieval more efficient. Disk partitioning. Disk partitioning divides a physical storage device into multiple local logical partitions, each behaving as a separate storage unit. This allows different file systems to coexist on a single physical disk and improve data organization and security. RAID, Redundant Array of Independent Disk. RAID is a storage technology that combines multiple disks into an array to improve data redundancy, fault tolerance, and performance. There are several RAID levels with varying data distributions and fault tolerance characteristics. Virtual memory. Virtual memory is a management technique that utilizes a portion of the disk space as an extension of the main physical RAM. It allows the OS to run more programs simultaneously and handle larger data sets than the available physical memory. Page tables. Page tables are data structure used in virtual memory systems to map virtual memory addresses to physical memory addresses. This translation enables efficient memory access and management by the OS. Disk cache. The disk cache is a portion of RAM used to store frequently accessed data from the disk temporarily. It helps reduce the disk access time and improves overall system performance. File allocation table and master file table. These are file system data structures used in some older and newer version of Windows respectively to keep track of file locations and metadata. Input-output structures in an OS are the mechanism and data structure used to manage and facilitate communication between the CPU and various I/O devices. I/O operations are essential for interacting with the external world, including reading from and writing to storage devices, sending and receiving data from networks, and communicating with peripheral like keyboard, mice, and displays. The I/O subsystem ensures that these operations are efficiently coordinated, transparent to applications, and reliable. Below are some key components and concepts related to I/O structures. I/O devices. These are the physical hardware components used which data is transformed between the computer system and external devices. Examples include hard disk drive, solid state drives, network cables, USB devices, graphical cards, and more. Device drivers. Device drivers are software components responsible for abstracting the underlying complexities of specific I/O devices. They act as an interface between the OS and hardware, enabling the OS to communicate with the devices effectively. When an application requires an I/O operation, example reading a file from disk, it generates an I/O request. The OS takes these requests and manages them through the I/O subsystem. I/O scheduler. The I/O scheduler is a component of the OS that prioritizes and optimizes the order in which I/O requests are executed. It aims to minimize disk seek times and enhance overall system performance. Buffering and caching. Buffering involves temporarily storing I/O data in memory before it is transferred to or from an I/O device. Caching, on the other hand, retains frequently accessed data in a memory cache to speed up subsequent read operations. Direct memory access. DMA is a technique that allows certain I/O devices to transfer data directly to or from memory without involving the CPU. This reduces CPU overhead and improves data transfer rates. Interrupts. Interrupts are signals generated by I/O devices to request attention from the CPU. When an I/O operations completes or requires immediate action, the device sends an interrupt and the OS responds accordingly. I/O central blocks, IOCBS. IOCBS are data structure used to represent and manage I/O operations in the OS. They contain information about the I/O request, the status of the operation, and any necessary control data. Overall, the I/O structures in an OS are crucial for managing the flow of data between the computer system and its peripherals. They enable efficient and reliable I/O operations, helping the OS provide a seamless and responsive user experience while handling a wide range of input and output devices.
Computer system architecture. In this section, we introduce the general structure of typical computer system. A computer system may be organized in a number of different ways, which we can or categorize roughly according to the number of general purpose processor used. Single processor systems. Most systems use a single processor. The variety of single processor system may be surprising. However, since these systems range from PDA through mainframes, on a single processor system, there is one main CPU capable of executing a general purpose instruction set, including instructions from user processors. Almost all systems have other special purpose processors as well. They may come in the form of device specific processors, such as disk, keyboard, and graphic controllers or mainframes. They may come in the form of more general purpose processors, such as input output processor that move data rapidly among the components of the system. All of these special purpose processors run a limited instruction set and do not run user processors. Sometimes they are managed by the operating system, in that the operating system sends the information about their next task and monitor their status. For example, a disk controller microprocessor receives a sequence of requests from the main CPU and implements its own disk queue and scheduling algorithm. This arrangement relieves the main CPU of overhead of disk scheduling. PCs contain a microprocessor in the keyboard to convert the keystrokes into codes to be sent to the CPU. In other systems or circumstances, special purpose processors are low level components built into the hardware. The operating system cannot communicate with these processors. They do their jobs autonomously. The use of special purpose microprocessor is a common and does not turn a single processor system into the microprocessor. If there is only one general purpose CPU, then the system is a single processor system. Multiprocessor systems. Although single processor systems are most common, multiprocessor systems, also known as parallel system or tightly coupled systems, are growing in importance. Such systems have two or more processors in close communication, sharing the computer bus and sometimes the clock, memory and peripheral device. Multiprocessor systems have three main advantages. First one, increased throughput. By increasing the number of processors, we expect to get more work done in less time. The speed up ratio with n processor is not n. However, rather it is less than n. When multiprocessor cooperate on a task, a certain amount of overhead is incurred in keeping all the parts working correctly. This overhead plus compensation for shared resources lower the expected gain from additional processors. Similarly, n programs working closely together do not produce n times the amount of work a single programmer would produce. Second one, economy of sale. Multiprocessor system can cost less than equivalent multiple single processor systems because they can share peripherals, mass storage, and power supplies. If several programs operate on the same set of data, it is cheaper to store those data on one disk and to have all the processors share them than to have many computer with local disk and many copies of the data. Third one, increased reliability. If function can distribute properly among several processors, then the failure of one processor will not halt the system, only slow it down. If we have 10 processor and one fails, then each of the remaining 9 processor can pick up a share of the work of the failed processor. Thus, the entire system runs only 10% slower rather than failing altogether. Increased reliability of computer system is crucial in many applications. The ability to continue providing service proportional to the level of surviving hardware is called graceful degradation. Some systems go beyond graceful degradation and are called fault tolerant because they can suffer a failure of a single component and still continue operation. Not that fault tolerance requires a mechanism to allow the failure to be detected, diagnosed, and if the possible corrected. The HP non-stop systems uses both hardware and software duplication to ensure continued operation despite faults. The system consists of multiple pairs of CPU working in lockstep. Both processors in the pair execute each instruction and compare the results. If the result differ, then the one CPU of the pair is at fault and both are halted. The process that was being executed is then moved to another pair of CPU and the instruction that failed is restarted. This solution is expensive since it involves special hardware and considerable hardware duplication. The multiprocessor system in use today are two types. Some systems use asymmetric multiprocessing, in which each processor is assigned a specific task. A master processor controls the system. The other processor either look to the master for instruction or have predefined tasks. This scheme defines a master-slave relationship. The master processor schedule and allocates work to the slave processors. The most common system use symmetric multiprocessing, in which each processor performs all tasks within the operating system. SMP means that all processors are peers. No master-slave relationship exists between the processors. An example of SMP system is Solaris, a commercial version of Unix designed by Sun Microsystems. A Solaris system can be configured to employ dozens of processors, all running Solaris. The benefit of this model is that many processors can run simultaneously. N processors can run if there are n CPUs without causing significant deterioration of performance. However, we must carefully control input-output to ensure that the data reach the appropriate processor. Also, since the CPU are separate, one may be sitting idle while another is overloaded, resulting is inefficiencies. These inefficiencies can be avoided if the processor share a certain data structures. A multiprocessor system of this form will allow processors and resources such memory to be shared dynamically among the various processors and can lower the variance among the processors. Such a system must be written carefully, as we shall see in chapter 6. Virtually all modern operating systems including Windows, Windows XP, Mac OS X, and Linux now provide support for SMP. The difference between symmetric and asymmetric multiprocessing may result from either hardware or software. Special hardware can differentiate the multiprocessors, or the software can be written to allow only one master and multiple slaves. For instance, Sun's operating system Sun OS version 4 provides asymmetric multiprocessing, whereas version 5 is symmetric on the same hardware. A recent trend in CPU design is to include multiple compute core on a single chip. In essence, these are multiprocessor chips. Two-way chips are becoming mainstream, while N-way chips are going to be common in high-end systems. Aside from architectural considerations such as cache memory and bus contention, this multi-core CPU looks to the operating system just as any standard processors. Lastly, blade servers are a recent development in which multiprocessor boards, input-output boards, and networking boards are placed in the same chassis. The difference between these and traditional multiprocessor system is that each blade processor board boots independently and runs its own operating system. Some blade server boards are multiprocessor as well, which blurs the lines between types of computers. In essence, those servers consist of independent multiprocessor systems. Cluster systems. Another type of multiple CPU system is that cluster system. Like multiprocessor systems, cluster system gather together multiple CPU to accomplish computational work. Cluster systems differ from multiprocessor systems, however, in that they are composed of two or more individual systems coupled together. The definition of the term cluster is not concrete. Many commercial packages wrestle with what a cluster system is and why one form is better than another. The general expected definition is that clustered computers share storage and are closely linked via a local area network or a faster interconnect such as InfiniBand. Clustering is usually used to provide high availability service. That is, a service will continue even if one or more systems in the cluster fail. High availability is generally obtained by adding a level of redundancy in the system. A layer of cluster software runs on cluster nodes. Each node can monitor one or more of the others. If the monitor machine fails, the monitoring machine can take ownership of its storage and restart the application that were running on the failed machine. The user and clients of the application see only a brief interruption of service. Clustering can be structured asymmetrically or symmetrically. In asymmetric clustering, one machine is in hot standby mode while the other one is monitor the active server. If the server fails, the hot standby hot becomes the active server. In symmetric mode, two or more hosts are running application and are monitoring each other. This mode is obviously more efficient as it uses all of the available hardware. It does require that more than one application can be available to run. Other forms of cluster include parallel cluster and clustering over a wide area network. Parallel cluster allow multiple hosts to access the same data on the shared storage. Because most operating systems lack support for simultaneous data access by multi-host. Parallel clusters are usually accomplished by the users of a special version of software and special release of application. For example, Oracle Parallel Server is a version of Oracle database that has been designed to run on a parallel cluster. Each machine runs Oracle and a layer of software tracks access to the shared disk. Each machine has full access to all data in the database. To provide this shared access to data, the system must also supply access control and locking to ensure that no conflicting operation occurred. This function, commonly known as a distributed lock manager, is included in some cluster technology. Cluster technology is changing rapidly. Some cluster products support dozens of systems in a cluster, as well as clustered nodes that are separated by miles. Many of these improvements are made possible by storage area networks, which allow many systems to attach to a pool of storage. If the application and their data are stored on the SAN, then the cluster software can assign the application to run on any host that is attached to the SAN. If the host fails, then any other host can take over. In the database cluster, dozens of hosts can share the same database, greatly increasing performance and reliability.